At the end of the 1800s, Thomas Edison was already a really accomplished inventor, wildly famous, quite the showman, hardworking, brilliant, and a brute force tinkerer more than kind of a physicist. And Nikola Tesla was of the younger generation, also brilliant, also hardworking, much more awkward, not quite the showman. In fact, he had a somewhat debilitating OCD. He had every time he walked or did anything, he had to do it in factors of three. So 27 steps, 9 steps, and that kind of thing. Kind of an awkward fellow, asexual, and a bit of a geek. Tesla comes over to America to work for Edison, and he comes equipped with a letter from a common friend of theirs who says, "You need to hire this guy Tesla. He's really good. He's a Serbian. He comes over. He's not particularly wealthy. In fact, he's pretty much broke. And he comes over, and Edison says, sure, you can work for me." So Tesla is continually trying to talk Edison into moving towards alternating current. Tesla believes it's a better way to go. Edison, who owns all the patents on direct current, prefers to ignore Tesla. And at one point, their kind of conflicting styles come to a head. Edison, faced with an engineering problem, says to Tesla, "Look, if you can fix this, I'll give you $50,000. And keep in mind, this is $50,000 in 125 years ago, so it's quite a bit of money." And Tesla fixes the engineering problem, and Edison says, "Huh, that's great." And Tesla says, "Where's my money?" And Edison says, "No, that's not what I meant. I just was saying like a figure of speech, like I'll give you $1,000,000." And Tesla says, "Well, I know how that sounds like. That didn't sound like what you said. You said you really were going to give me 50,000. So Edison says, "You're fired." And Tesla says, "You can't fire me. I quit." And Tesla goes to digging ditches, literally digging ditches to get by, to scrape by with another company. And Edison continues on his quest to become the utility company. See, Edison was a famous inventor, but he was trying to make a kind of a transition that we've seen, for instance, Steve Jobs make from inventor to kind of captain of industry. So Edison wants to become the utility that provides electricity to the world, not just the U.S., but in Europe as well. Tesla works his way up the kind of ditch digging world, and it becomes clear after a year or so that to his superiors that he's someone that needs to be reckoned with. He's a mind that needs to be harnessed, and he's introduced to George Westinghouse, that George Westinghouse from the Westinghouse Corporation, who had made his money as an inventor of an air brake for a locomotive. So Tesla talks to Westinghouse. He's like, "Look, we need to go alternating current." And he explains the advantages, and Westinghouse says, "Let's do it." And they go into competition with Edison, who's busy supplying cities all over North America and Europe with direct current. Now, many times it's not just cities. It could just be a building. Like, in other words, it wasn't necessarily an entire municipality that would sign a contract. So this was part of Edison's vision, was that there would be kind of local supply of electricity. Tesla had a different vision. He had something a little bit more remote that would supply entire regions. So this went on, and eventually, of course, Tesla's alternating current won out. And it wasn't like this happened in obscurity. I mean, this was bigger than Mac versus PC. This was bigger than Beta versus VHS. The entire country was actually following these two figures and trying to figure out which one, whose power would win. Now, here's my question. Why did alternating power win? If you think you have an idea, you can hit pause and kind of formulate an answer. But if you don't worry, we're going to get to it. Go ahead and do number 52. Number 52 reads, for a residence, a circuit includes 4 100-watt lamps, 5 200-watt receptacles, and 4 75-watt lamps. A reads, how many total watts are used in this circuit when fully loaded? B reads, given that the circuit is standard 120 volt, what should the amperage for the circuit be? Assume a power factor of 1.0. Go ahead and hit pause. Now, if we're talking about electricity, as in so many areas of building science, there's a water analogy. Although water and electricity really aren't friends in real life. So you have the battery, which produces the voltage or the pressure. Voltage is pressure, and indeed, during Edison's day, they actually called voltage electrical pressure. That voltage sends the electricity through a wiring, a conductor, as current. Current is equivalent to like the pipe size, the flow. So, and literally a bigger wire will carry more current. and then it goes across a resistor. A resistor can be, in our case, it can be a lamp, a light bulb. And there's a switch to, when it's connected, it connects a circuit. Electricity is the movement of free electrons in a medium. And it's the movement part that makes the whole thing work. It's not the electrons, it's the movement of them. So in the equivalent water analogy, we have a pump, we have a flow, we have friction, and we have a valve. Now the analogy isn't perfect, because if we take out the resistor, if we take out the light bulb in the electrical example, the whole system becomes really unstable. It starts to heat up really quickly. It can cause electrocution or fire. It's a short circuit. If we take out the friction element in the pump, it's still, somewhat stable. But anyhow, it's a pretty good analogy, and it can hold. And so what we want to know is we want to say, okay, electricity is a movement of free electrons. So what kind of materials have a lot of free electrons? And the answer is metals. Now, which metals have the most free electrons, are the best conductors? Actually, the best one is platinum. Second most, platinum's kind of expensive. Let's go to second most. Well, that's gold. Well, let's go down to third. Well, third's silver. But eventually we kind of get to what's pretty close to a tie for fourth, which is aluminum and copper. Now, are we going to use aluminum or copper in our wiring? It generally depends on the price of aluminum and copper right now. That's basically what determines it. For a while, we thought that we were using both. And it occurred to us that aluminum develops a film when it's exposed to air. And that film, in some occasions, can cause fire. So we stopped using aluminum. And then after a while, we said, well, I think aluminum actually is okay. So we started using aluminum again. And then we said, oh, the fires are starting again. Maybe aluminum's a problem. So aluminum is still used, but it only can be used by a qualified electrician. Regular folk, lay folk who are working in electricity kind of on their own homes, need to use copper because copper doesn't develop that film, but electricians know how to deal with that. They also have copper-clad aluminum if the price of aluminum is enough lower than copper and you don't want to work with the film. So if we draw a battery here and we're going to have a positive and negative end of the battery, the positive end is going to have more electrons, more free electrons. It's going to go through a conductor. The conductor is often going to be wrapped in an insulator, which is a material that has few free electrons, like plastic. And then it's going to go through a resistor, like a light bulb, which in our next section we'll start to call a lamp. And it'll come back to the negative side. And this is direct current. Batteries run on direct current. The electrons will move through the conductor. It'll move across the resistor, the light bulb. The light bulb will light up. And then it'll return. And eventually the pressure, the voltage, in the positive and negative ends of the battery will be even. So there'll be no more potential. There'll be no more kind of extra pressure. And then the battery will be dead. And if we recharge it, it'll move the electrons back over to the positive side. But if we don't, the battery's dead. And that's direct current. Now, alternating current is a bit different. In alternating current, we're taking a power source. We're moving it across the resistor. And then back again. Back and forth. Back and forth, back and forth. In the U.S., we move it back and forth 60 times per second. In parts of Europe and parts of the Middle East, it's 50 times per second. That's why you need the adapter. Anyhow, so let's take a look at the problem that we started, number 52. For a residence, a circuit includes 4 100-watt lamps, 5 200-watt receptacles, and 4 75-watt lamps. How many total watts are used in this circuit when fully loaded? That's a pretty straightforward answer. We'll take 4 times 100-watt lamps is 400. 5 times 200-watt receptacles is another 1,000. And 4 times 75-watt lamps is, again, 300. So we'll add 1,000 to 400 to 300. We get 1,700 watts. 1,700 watts. Now, to do part B, you actually need to know Ohm's law. Part B says, given that the circuit is a standard 120 volt, that's what comes out of the wall in our buildings in the U.S., what should the current amperage be for the circuit and assume a power factor of 1? Well, Ohm's law looks like this. W, which is the power as measured in watts, equals I, which is the current as measured in amps, times V, which is the voltage, which is like the pressure, which is measured in volts. So watts is like the gallons per minute coming out of the hose. And I, the current measured in amps, is like the size of the hose. And V, the voltage measured in volts, is the pressure in the hose. And so, again, we want to understand the relationship of the math. If we double the amperage, if we increase the pipe size, if we increase the amps, what are we doing? If we double it, what are we doing to the watts? We're doubling it. If we double the voltage, we're also doubling the watts. If we double the voltage and double the amps, we're doubling both. So using that formula, we say, okay, 1700 watts equals some current times a known voltage, our standard 120 volts coming from the socket. And we solve for that, and we divide 1700 by 120, and we get an amperage of 14.2 amps. Now we can look at a chart, and now amps, remember, is like the pipe size. So we can look at a chart, and the chart will say that a 15 amp circuit uses a number 14 gauge wire, and the actual size is about a 1/16 of an inch. And a 20 amp circuit requires a number 12 gauge wire. Remember, in metal, as we go lower in number, in gauge, we get thicker. And the actual size is a little bit bigger. It's 0.8 inches. And this goes all the way up to 200 amps. At around 200 amps, our conductor size is called double knot, 00, and it's about 1/3 of an inch. So as we get more and more current, we need a bigger and bigger wire. Now here's the problem. Big wires, high amperage circuits, over long distances they get hot and they leak their electricity to electromagnetism. That'll be important later. So let's say that for the town that you're in or the neighborhood you're in, maybe it requires 1,000,000 watts, 1,000,000 watts. So given that, at 120 volts, how many amps do we need to supply 1,000,000 watts? So you have 120 volts, you have 1,000,000 watts. How many amps do we need? Go ahead and hit pause. So running out the math, we have 1,000,000 watts equals some current times our pressure of 120 volts. Now, solving for amps, we get 8,333 amps. Here's the problem. If we want to supply 8,333 amps, well look, if 15 amp is about a 1/16 of an inch and 200 amp is about 1/3 of an inch, our telephone poles to supply your neighborhood or your city, to supply that 1,000,000 watts at 120 volts, you'd have like cables, the diameter of school buses being strung from pole to pole. That makes no sense. We can't do that. First of all, it's too heavy. Second of all, it's too expensive to do. And third of all, we can't run long distances on high amperage. We already said that. If it's a big pipe, we can't run a long distance. It gets too hot and it leaks too much electricity on the way. So we got to figure out a better way to do it. Now we could just supply it at higher voltage. So let's figure it out now. Let's do 1,000,000 watts at 60,000 volts. Now, what's the new amperage going to be? So to figure out the new amperage, we'll divide both sides by 60,000 and we'll find out that the new amperage is about 16.7. Perfect. So what we'll do is we'll just run 60,000 volts at 16.7 amps. That works out. So we can just run the 60,000 volts right to the outlet. Why can't we run the 60,000 volts right to the outlet? Well, because we'd have lightning from the socket. We wouldn't even be able to get close to an outlet without getting electrified. See, if you take a 9-volt battery and you stick your finger across both poles in the battery, your finger doesn't have enough free electrons to be moved by the 9 volts in the battery. There's not enough voltage. But if you stick your finger, in a socket, there's enough voltage there at 120 volts. There's enough pressure. There's enough pressure to push the electrons across your finger. So there's always this relationship between higher voltage is more pressure, and it allows, and like I said, in Edison's day, they used to call it electrical pressure, and it allows the electrons to jump farther because it's under higher pressure. You can look at this image to get a sense. You have the volt kind of pushing the amp through, and the ohm, which is a resistance, which we haven't talked about too much, is kind of crimping it down. But the more voltage, the more pressure. So there's always this kind of balance. On the one hand, we want really high voltages to run long distances, to run power long distances. But on the other hand, we want really low voltages to make sure we don't get electrocuted in our buildings and make sure fires don't start and keep property safe, keep equipment safe. So how do we do this? Well, this is the crux of why Tesla won and Edison lost. Because when you run high voltages, you need to be able to step them down. So what we'll do is we'll start at the power plant and we'll produce, say, 60,000 volts. Now, it could be as high as over 700,000 volts. It could be something like 30,000 volts. But we have these regional feeders, these high voltage transmission lines. They kind of look like giant erector sets, and they dot the landscape. They're really, really tall, high off the air. Of course, they're high off the ground because we don't want the voltage. The voltage is so high, we don't want the power to arc. Because in the power lines, I think we always think of them as wrapped in an insulator, but they're not. They're live. They're totally live. And the electrons are moving through them and really want to go to the ground. So if you get close enough, it'll jump out and it'll kind of it'll meet something else that touches the ground. Now, birds can rest on these, no problem, because they're not touching the ground. The birds don't possess the best path for the electrons to go through. So if a bird was in theory, actually it happens with squirrels sometimes. So if the squirrel is in theory, the tip of his tail is touching the hot wire and his nose is touching the pole that supports it, the squirrel will get zapped because he's produced now a better path for the electrons to move to the ground. Anyhow, they're going to move across the country at tens of thousands, sometimes hundreds of thousands of volts from the power plant. Then they're going to go to these power substations. Now, in cities, these are generally out of view, but in most of America, you see these kind of everywhere. They're usually about a half a block big or a quarter block big. They have gravel. Everything is painted a certain color gray. They're fenced in with barbed wire because they don't want people jumping them. And they're every, so many miles. There's one of them. And what the job of that power substation is to do is to step down the voltage, to take it from, in our example, 60,000 volts down to, in our example, 12,000 volts. Now, 12,000 volts is still plenty of voltage. It's still unsafe, but it's not so unsafe that it can't run underground around the city. It's not so unsafe that it can't run on wooden poles around the city. So it'll go on wooden poles at maybe 12,000 volts, although the number could be different. It could be 3,000, it could be 15,000. And it'll go around until it hits the buildings. And once it hits the buildings, there's another transformer. Again, the transformer steps down the voltage. So the voltage will be stepped down to 120 volts before it goes into your building. Then it goes into your building at 120 volts, and it comes out the outlet at that much safer voltage level. Now here's why Tesla won, and here's why Edison lost. At least at the time, we didn't have the equipment to step down voltage. We didn't have transformers that worked with direct current. We only had it with alternating current, which meant that this kind of trade-off where we're taking power around the country at high voltages and stepping it down to lower voltages, that system didn't work in Edison's world. In Edison's world, the power plant there'd be a power plant every few blocks. That power plant would generally be a small generator, and it would be supplying the buildings around it. Then another few blocks would be another generator, because we couldn't take direct current too far, because if we took it too far, we need too much wattage. If we need too much wattage, we need bigger pipes. We need more amperage. If we need more amperage over long distances, we have too much heat buildup and too much electricity lost to electromagnetism in the transmission. So in Edison's model, it was a distributed model where there were power plants kind of everywhere. And you could see why Tesla's model was superior at the time, because